In standard single-variable calculus, we measure how a function changes using the first derivative. It acts like a speedometer, giving you a single number to represent the slope of a line at any given point. But physical environments are rarely restricted to a single variable. Tracking temperature, pressure, and wind speed simultaneously across a 3D atmosphere makes a single slope inadequate. You need to track how multiple inputs produce multiple outputs all at once. To manage this, we use the Jacobian matrix. It acts as a mission-controlled dashboard, taking the first-order partial derivatives of all those interacting variables and organizing them into a single mathematical structure. The core function of the Jacobian is local linear approximation. If you take a complex, highly warped mathematical space and zoom in incredibly close to a specific intersection, that space appears perfectly flat. The Jacobian mathematically represents that flat plane. By structuring the partial derivatives into an m by n grid of rows and columns, it captures exactly how the space around that specific point is stretching, squishing, or rotating. This transforms dense, nonlinear, multidimensional chaos into local, manageable linear approximations that we can easily calculate. While the Jacobian tells us the slope, or where we are going, we also need to know the shape of the road itself. We need a way to distinguish between the bottom of a bowl-shaped valley and the plateau of a mountain pass. For this, we build the Hessian matrix. It operates as the multidimensional equivalent of the second derivative, organizing all the second-order partial derivatives into a square n by n grid. Let's calculate the curvature for a specific altitude function with two inputs, f of x, y equals x squared minus y squared. Step 1 is deriving the gradient using the first-order framework from the Jacobian. We find the slope for x is 2x and the slope for y is negative 2y. Step 2 requires taking those gradient values and deriving them a second time to build our 2x2 Hessian matrix. The x squared derivative of 2 goes into the top left slot, and the negative y squared derivative of negative 2 goes into the bottom right slot. Because of Clairaut's theorem, we know that for any smooth function, the mixed derivatives evaluate to 0. We place zeros in the remaining slots, creating a perfectly symmetrical matrix. This symmetrical grid mathematically encodes the intricate curvature of every interacting dimension. To read that curvature, we extract the eigenvalues from the Hessian matrix. These act as the core structural multipliers, revealing the exact physical shape of the surface. If the eigenvalues are all positive, the multidimensional space curves upwards in every direction. This forms a bowl shape, meaning you have found a true local minimum. If the eigenvalues are all negative, the space curves downwards, creating a hill shape. You are standing at a local maximum. Look at the geometry of our function. F of xy equals x squared minus y squared. Pause the video and deduce what mix of eigenvalues must exist to create the saddle point. A saddle point exists because the matrix produces a mix of positive and negative eigenvalues. The surface curves upwards along the x-axis, but downwards along the y-axis. Without calculating the eigenvalues of the Hessian, you could mistake a flat section of a saddle point for a true minimum and stop searching entirely. Training a modern neural network requires finding the lowest possible point of error in a landscape that spans millions or billions of mathematical dimensions. The gradient, derived from the Jacobian framework, acts as the compass. It calculates the initial slope and points the AI strictly in the direction of steepest descent. The Hessian acts as the suspension system. Using optimization techniques like Newton's method, the Hessian evaluates the curvature of the landscape. It signals the AI to take massive leaps when crossing wide, gentle bowls, and to switch to careful microsteps when dodging a volatile saddle point. This maps a direct progression from the basics of single-variable calculus through the gradient and Jacobian into the multidimensional curvature of the Hessian, ultimately driving deep learning optimization. The Jacobian maps the relationship between multiple inputs and outputs. The Hessian measures how that exact relationship curves. Together, they give us the tools to navigate and optimize the invisible geometry of complex systems.